Today we're going to talk about a class of algorithms that's been used in deep generative models, notably in a Bayesian context. It's usually presented as a clog, a gear in the variational autoencoder. But really what it does is it takes two very general ideas, amortization and variational inference, and combines them. And today we want to think about what is the scope of application of amortized VI, and whether we can think of it as a general purpose inference algorithm. So as a motivation, I'm just going to introduce the latent variable model. And the characteristic here is that for each of my observations x, I'm going to have an associated latent variable model, and then also some global parameter that's common to every observation. So one example would be, let's say we're running a clinical trial, and we have observations across different patients. Then for each patient, I'm going to estimate a characteristic, like their physiological parameters, let's say. But I'm also going to have some characteristics that are common to all the patients, right? And oftentimes, what you might do is you might estimate a population behavior, and then your latent variable would be deviations from the average behavior. Here's an example that's a bit more ML from visualization. So I have a bunch of images. My observations is going to be the color channels across the different pixels. My latent variable is going to be a low-dimensional representation of each images. But then what I'm going to have is a neural network that allows me to decode the low-dimensional representation back into an image. And so theta here is going to parameterize my neural network. But it's common to all the observations because the decoder is the same for all the images. It's not image-specific. Right? OK, so the general problem of inference is, given some observations that we have, we want to learn the unknown variables. And there are various approaches to do that. So one might be I try to maximize a marginal likelihood, or maybe I'm Bayesian, and then I'm going to try and estimate a posterior distribution. But whether you're doing one or the other, you have this problem of estimating an intractable distribution, right? And I'm going to focus on the Bayesian case, which is a bit closer to my work, but also a little bit more general, it turns out. So there are a lot of ways to try and approximate a distribution. One of them is variational inference. And what variational inference says is I have a family of tractable distributions. Let's call it Q. Those distributions are well-behaved. I understand what they do. And within that family, I'm going to try and find the distribution that best approximates my target distribution. Right? And in order to do that, I need to solve an optimization problem, and I need to define a notion of agreement between different distributions. Right? So we're going to use the Kullback-Leibler divergence, written out here. And there are a lot of ways to think about this divergence, but also it's not that intuitive, it turns out. The one thing I will point out is that this divergence is 0 if and only if my two distributions are equal to one another. But other than that, when the KL divergence is not 0, it's not super clear what's going on, right? And in fact, you have a lot of different divergences or distances that are going to verify this property, that they're 0 if the two densities are equal, but then start behaving in very different ways. And so that changes the optimization problem that I'm solving and the solution. So the next thing we need to determine is what family of approximation are we going to use? And we typically use a parametric family. Right? So what that means is my distributions are fully defined by a finite number of parameters. So if I have a Gaussian approximation, that would be the mean and the variance. And then I solve my optimization problem with respect to those parameters. One family that people often use is the factorized or mean field approximation. And the idea here is that the factors for each latent variable are going to factorize. So I'm going to treat my unobserved variables as though they were independent. Now, obviously, we don't expect this to be the case, and it rarely is the case. It's a computational hack. And the reason why that is then the number of variational parameters that I need to learn scales linearly with the number of observations. if you're trying to, let's say, fit a dense Gaussian distribution, suddenly you have something that scales quadratically with the number of observations. And then you have things in between. And there are the reasons why this optimization problem becomes difficult. Okay, but what is the price that I pay because I am using a factorized approximation, and B, the objective function that I chose, which is the KL divergence? All right, so here's an example. This is the simplest example you can treat, where I'm going to approximate a Gaussian distribution where the terms are not independent, so you actually have correlation, with a factorized Gaussian. And you can see that there is a mismatch between the approximation and the target, even once you find the optimal solution. This example, actually, there's a lot of counterintuitive results you can get from analyzing it. What I will say is that you still get accurate estimations of the expectation value, but then you will underestimate various measures of uncertainty, such as the variance or the entropy. And now it turns out that as the dimension of the problem grows, you can get very, very good estimates of the entropy, but arbitrarily bad estimates of the variance in different directions. So whether this method is appropriate or not really depends on what we're interested in, right? What characteristics of the distributions we're going to be interested in, right? And now what's interesting is if I were to compute the KL divergence in the other direction, so from P to Q as opposed to from Q to P, I almost get an opposite behavior, which is that I get very good estimates of the variance, but arbitrarily poor estimates of the entropy. Yes, question?
Minimizing the KL versus the reverse KL, are those, is one computationally more convenient than the other, or why do people try both? I know, I've read how they have, I think there's mean seeking or mode seeking, but practically speaking.
Yeah, absolutely. So practically speaking, this is extremely difficult to do, and it doesn't scale in high dimensions. So people do this because that's the option they have. And the reason why this is easier to do is because if I go back to this definition, really what I'm computing is an expectation value with respect to my approximating distribution. So what I'm going to do is I'm going to construct a Monte Carlo estimator by drawing sample from this distribution. If I compute the KL divergence in the other direction, I'm computing an expectation value with respect to my target distribution, and I don't have a cheap way to draw samples from my target distribution. Right? The cheap way would be, the cheapest way might be to do MCMC, but once you're able to do MCMC, you no longer need to do variational inference. Yeah. So that's the reason. And I think that, the choice of how VI is implemented is computational, rather than this objective function behaves in a way that's pertinent to our problem. Yeah. And now I'm going to add another ingredient, which is amortization. Right? So amortization, really what it does is it says, I'm going to change again the family of approximation that I use. And kind of the motivation is, well, right now, for each of my factor, I am learning a different parameter, right? But maybe those parameters have some things in common, and I don't need to learn all those parameters separately, right? And the intuition is what distinguishes the different factors is the observation that they correspond to. So maybe I can learn a map from my observation to my variational parameter. And so once you do that, you introduce an inference function, and now instead of minimizing your objective function with respect to your variational parameters, you're going to minimize it with respect to the parameters of your inference function. And so the question is, if I do this, right, is my optimal solution going to be as good as if I were doing factorized variational inference? And how is this going to change my optimization problem? So it turns out that, first things first, your optimal solution is not going to be as good. Right? There's something called the amortization gap. And the way to see this is that any family that exists in my amortized family, I can actually find it in my factorized family. Right? How do you do that? You just apply your inference function, and then you match your variational parameter to the output of that inference function. Right? And so therefore, this QA, this amortized family, is a subset of the factorized family. It's actually a strict subset. I haven't demonstrated that, but there will be hints in the talk as to why that is. Something to keep you on your feet. Okay, and so the consequence of that is that the best scale divergence I achieve with my factorized family is going to be better than whatever I can achieve with my amortized family in general. But now the hope is that, okay, I have a subset, but maybe this is the subset that I need. And within that subset, I'm actually going to have the solution. And so the condition for that to be true is if you can find an inference function that solves the interpolation problem between the observation and the optimal variational parameters returned by factorized variational inference. This is the condition under which you close the amortization gap. And so in that case, you achieve the same optimal solution. So let's look at an example of this in action. So this is the linear probabilistic model. It's the simplest generative model, hierarchical model that you can construct. And the nice thing is you can actually work out the posterior and the solution of VI analytically over a few pages of algebra. And the solution is the following, which is that my optimal expectation is going to be a linear function of xn, but it's also involving the mean of all my observations. Right? So somehow, at first glance, it doesn't look like it's just a function of my local observation. Right? And this is actually a property of the posterior distribution itself, which is that the posterior distribution of my local latent variable doesn't only depend on xn. This is a phenomenon called partial pooling. Right? And actually, it's a very desirable feature. So let me give you an interpretation from a modeling perspective. Right? And then we'll quickly see why the math leads us to this result. So I'm going to go back to my clinical trial example. Right? So all the Zn's are now physiological parameters. Yes?
One quick thing.
Yeah, absolutely.
The first line, mean.
Yes. So I'm using a flat prior. Right? So what that means is, so in a Bayesian model, I'm supposed to specify a prior distribution on my parameters. So here what I'm saying is I'm not explicitly going to specify a prior. Right? So I'm not going to give any preference to any distribution. The reason I do that is not because you should use flat priors. It's because it made the math a little bit simpler. And then you recover some interesting edge cases. Yeah. Any other questions? OK, good. So I'm going to go back to my clinical example. And basically what this partial pooling, this sharing of information tells me is that somehow the inference I do about the physiological parameters of patient 1 is informed by the data I have about the other patients. Or another way to do it, another way to view it, is that what I learned from one patient tells me something about the other patients, right? So you have this combination of a local influence and a global influence, right, that are being at play. And now mathematically what's happening is if I write down, if I want to get the expectation value of Zn given x, I do this integral. This integral is going to involve the global parameter that is shared across all patients. And to learn that global parameter, I need to use the data from all the patients. OK, so did we doom our amortized variational inference scheme? Well, I'm going to claim that you can still learn an inference function. And not only that, even though you have this x bar term, you can learn a linear inference function. And so if you do that, so now I'm going to fit a model. I have 10,000 observations. I'm going to use polynomials as my inference functions with various degrees. Constant is degree 0. D equals 1 is a linear function. D equals 2 is a quadratic. The black line is going to be my factorized variation inference. Eventually, it's going to converge to the optimal solution. But then, as you can see, once I start using a linear or quadratic function, I'm actually able to recover that optimal solution. Not only that, I do it faster. Not only that, I do it by using 3 variational parameters, and that is completely independent of the size of the data. Right? So I have the number of the parameters I need to learn doesn't scale with the number of observations that I have. It scales with the complexity of the inference function I need to learn. Now, I don't have a formal proof that this is always true. I have empirical evidence that points towards that. OK, the other note that I will make is that on average, So we repeat this experiment multiple times. On average, using the well-parameterized inference function, so linear as opposed to quadratic or over-parameterized, yields the fastest convergence. We will see that that's not always true if we start using neural network as opposed to polynomials. Yes?
What do you think the curves would look like if you had b equals 3 and 4 and so on?
I think you would get more variation in the initialization, right? The iteration, the time to convergence, might change a little bit, but at some point you start paying more computational cost per iteration. So there's a bit more depth to that particular problem. Okay, so now why does this work? Okay, so I want to point out that this condition, that the posterior only depends on xn, is an unnecessary condition. The necessary condition on the model is that there exists what we're going to call a data-dependent learnable function. But really what I'm saying is there exists a function. And here I want us to go back. I'm not saying it has to be a smooth function or a well-behaved function. I'm just saying there must exist a function. And so if we go back to the definition of a function, what that means is if x1 equals x2, then they must have the same optimal variational parameters. Right? That's all I need. It's actually a very big constraint. But it's not as big as the constraint up there. So in the linear probabilistic model, my optimal variational parameter is a linear combination of xn. Granted, this intercept depends on x. But that's fine. I'm still verifying the condition that every time x1 equals x2, I also have nu star 1 equals nu star 2. Now, of course, there's another necessary condition, which is that my family of inference function needs to be rich enough so that I can find an inference function that solves the implicit interpolation problem between the data and the optimal variational parameters. And so the focus on the literature has been on this latter necessary condition, but that's because people were only thinking about amortized variation inference in some very specific context. Once we start thinking about it as a general purpose algorithm, we have to start worrying about the first condition. So I'm going to go back to my initial generative model. It turns out that this particular model is a simple hierarchical model. If you want to be precise, it's a simple hierarchical model in a non-centered parameterization. And you can demonstrate that there always exists a learnable function between my local observation and my optimal variational parameters. Not only that, you can have a more general result that shows that this is true between your observation and your true posterior density. So forget about variational inference. Any approximation procedure, any inference procedure that inherits this property from the posterior distribution is going to be amenable to amortization in the sense that there's some hope that I can close the amortization gap. And as I said, empirically, we find that the number of parameters I need in my inference function to close the gap does not scale with the number of observations. So here's another example where this time I have a nonlinear, and instead of using a polynomial, I'm learning an inference neural network. And the one result that I will point out here is that actually we know that for this example, so you have 2 layers of width 4, you're able to close the gap. So it's a relatively simple example. Now, if I start increasing the width of the neural networks, right, I'm over-parameterizing, but it turns out that when you do that with neural networks, you start getting better convergence, faster convergence. Right? So it's not just about controlling the number of parameters, and there's more that happens about how we're changing the optimization problem here. Right? I leave that as a somewhat open problem, but we have observed with neural networks that over-parameterized neural network can perform better in terms of optimization. All right, here's another example. So now I'm going to complicate a little bit. This is a saw time series, and what it's saying is that my latent variable now depends on the realization of my previous observation. So in that case, still a latent variable model, you actually don't have an inference function. An inference function does not exist. And the reason why that is because x1 equals x2 does not guarantee that they're going to have the same optimal variational parameters. However, this is a pretty friendly example. If you expand the domain of your inference function to take in both the local observation and the previous observation, you're able to close the amortization gap. All right, hidden Markov model. So now my latent variable depends on the previous latent variable. Any guesses as to what happens here? Is there an inference function, yes or no? A learnable inference function. Yes? Let's have a show. Who thinks there is a learnable inference function? Okay, a few people. Who thinks that I need to expand the domain in order to have a learnable inference function? Okay. Who thinks there does not exist a learnable inference function? All right, and that's why you should read the paper. Because there does not exist a learnable inference function from any subset of x to your optimal variational parameters. And so the reason why that is because, so if I think back about my simple hierarchical model, right, the linear case, my solution was some combination of a global influence, that was my sample mean, plus a local influence, right? So I had this notion of a local influence, and then the global influence gets absorbed into the coefficients of my inference function. Here, that sense of some of the data is local and some of the data is global breaks through, right? Because each data point is going to be local to a various degree to each latent variable. Right? So just using the data as would be prescribed by a traditional amortization scheme, you're not able to get the solution, right? And the way you prove this is you can construct some counterexamples that are not too non-adversarial. You get a similar result for a dense hierarchical model, right? So one example of that would be for a Gaussian process. And here it's the same reasoning, is that my latent variables are going to be influenced by the observations that are close, right? Geographically or by whatever metric you want to use, but less so, but still to a varying degree for the observations that are far away. Okay, so I realize we're already in injury time, but I want to point out that that's because we had questions and interruptions, right? So just two references that are coming out. So one is a paper with Lawrence Sol, who is also at the CCM, and that one is focused about what happens when I use a factorized approximation for a dense Gaussian, and it really examines that example, which you'd think it's the first example you see in a textbook from 20 years ago. It turns out they didn't look at what happened as you increase the dimension, and you start getting unexpected results, right? And then the other paper has the same title as the slides. It's in preparation. I expect we'll have a preprint out soon. I just want to summarize the main themes that I hope will spark some discussion. One is we have all these measures of disagreement between distributions. We know what they mean when they're zero. But what do they mean? How do we interpret them when they're non-zero? And in most applications, we're going to end up with something that's non-zero, right? So what choice of objective function should we make? Then when can we close the amortization gap? So here I try to argue it has to be both a property of the model and of the inference. So deep generative examples, turns out that property of the model is verified, but that won't be true in general. And of course, there are some questions about what are we doing to the optimization when we're changing from optimizing an inference function as opposed to the parameters directly. And there's, of course, this idea of now we want to generalize, right? We want to apply the inference function that we learned to new data, right? So people do that to measure the capacity of their model on held-out data. I think there's a problem here about how exactly is this problem defined? Is it an online learning problem? Is it a out-of-sample prediction problem? Is it a quasi-Bayesian inference problem? Right? So I want to investigate that. And with that, I open the floor to questions.
Any question? Yeah, Case?
There's very clear and clean categorization of what model have learnable function or not here in this, but in astrophysics people just there's this model that's good, put this together, and at some point it become mumbo jumbo. Do you think there is a general framework that we can just deploy? When someone make a bold claim and I want to debunk that, and I just take their model, do something about it, and say, oh, this is a hidden Markov model, their host.
Yeah, I think you can exactly do that, right? So the nice thing is that this property of the model is a verifiable property, right? And so we kind of demonstrate how you would verify this property. And again, like I said, all those proof techniques, not only do they apply to variation in mean field, they apply to the true posterior distribution. Right? Now, what I will say is the simple hierarchical model, once I start, all I need is conditional independence in the likelihood. Right? But leading up to that conditional independence, I could throw a neural network that's extremely expressive. So in a way, those features that you have of correlation, right, maybe in some ways you can replace those conditional dependencies with the conditional independence that's the output of a neural network. So I think that not only there are ways to identify the models where amortization is not going to close the gap, but there might be ways to modify the model to be more amortization friendly. The other thing that I will say is that all this analysis focuses on, you achieve the optimal solution. And in practice, sometimes you don't even come close, or you don't even know, right? And so then the question is, given a computational budget, how far do I get, and what is the better method? Like we have models where we know we don't close the amortization gap, but maybe that approximation is good enough and is better than what you can hope to achieve with some computational budget. So maybe the short answer is yes, and the longer answer is longer.
Yes. Sorry, behind you. Yeah. Yes. Yeah.
How much work has been done on? You showed the slide of where I believe there was some deep nets parameterizing the distributional parameters.
Yeah.
The variational distribution.
Yeah.
So how much work has been done on, the early stage training process, and even to know empirically if we're on the right track, what decisions we should make to track the progression of the variational distribution, to have theory for that,
Yep.
have empirical rules like, I should check this and check this, or I should double my capacity, or if I see this is the same, I'm okay.
Yeah. So I did a lot of MCMC during my I still do a lot of MCMC, and the theory we have for variational inference is not close to the theory we have for variational inference, and which that kind of theory for MCMC convergence, for checks, for heuristics, and so forth, right? That's what we would really want when we do variational inference, right? And so you run into all sorts of problems where you're sensitive to the initialization. You start plateauing, and then you jump to the next plateau. The nice thing about variational inference is that you've taken the problem of estimating a distribution, which traditionally is done through sampling, and you've turned it into an optimization problem. And so then you have hope that you can deploy a lot of the outstanding theory that exists about optimization and stochastic optimization to do this kind of thing. Now, in terms of the practical thing that people have done here, once you appreciate that an amortization gap exists, what people might do is initialize with amortized variational inference, and then switch to factorized variational inference, right? And that's something called semi-amortized variational inference. And that's a useful strategy because not only it can give you improved results, but it can also act as a diagnostic to verify this second condition, right? Because you know that if you don't improve, then you've saturated how expressive you need to be. But if you do improve, and maybe you can just evaluate a gradient to know that, there are some limitations to doing that, but then you know that, maybe with a more expressive inference function, I would see improvements in terms of KL divergence, right? And again, minimizing the KL divergence is not the end-all, be-all. I hope I've made that clear at the beginning.
We have some time for one last very short question.
Slides you mentioned HMM does not include this learnable function. But of course, I can just include all the X into the subset.
Yes.
So that must be like.
So I can construct a counterexample. Well, so yes and no. It doesn't quite work. So it kind of depends on how you include all the X's, right? But really, what you need at some point is you need to start worrying about indexing the X's and indexing the positions. And once you start indexing, So it's not just enough to have all the data. You also have to know the position of the latent variable in your hidden Markov chain. And so you can certainly do that. But actually, if you think about it, what factorized variational inference does is it learns an inference function from the index to the optimal variational parameter, right? It's just that instead of specifying the index, you specify your observation. And if all your observations are unique, those observations act as surrogate for the indices, right? So that's an example of you're just memorizing the input-output of your network. So with that, unless you do that, I don't see how with amortized variation inference you can do that. Right? And then, of course, you lose all hope of generalization. But again, generalization is, frankly, based on what I've read in the literature, a problem that deserves to be better defined, because there are a lot of ways to think about what this generalization could mean.